All right, guys. So we are learning the physical methodology lectures one on the September 13. Now we are pretty behind in the schedule, so we will study through this verbal session to catch up. The purpose is to study as much as we can. So in now on this slide we focus on the crystal, unit cell, lattice, and symmetry. So by definition, right? A crystal is a crystal is an orderly array of atoms in space. So, an orderly array of atoms in space, meaning that this is a complete structure, right? So, think about atomic structures, right? Atomic structures. This is a crystal. 3D, right? Complete with a lot of unit cells, of course. An atomic structure contain multiple unit cell and primitive cells and primitive cell. So atomic structures is a container that contain a lot of unit cells, and a unit cells is the smallest repeat unit in space that possessing the symmetry of crystal. So a crystal is a container of atom in space of an orderly. It has an order, right? An orderly array of atom in space. A container that contain arrays in a certain order in space, in spatial order, right? So, and unit cells is the smallest repeat unit in the crystal, right? And it follows a certain order. It possesses the symmetry of a crystal. And the lattice unit cells is the has the structures of unit cells is the lattice, because lattice is a regular geometrical arrangement of points or objects over an area or in space. So lattice, the regular geometrical arrangement of points or objects over an area or in space. In another word, lattice is the lattice is the bone of unit cell. It established the construction for the unit cell. And symmetry is the property of remaining invariant under certain changes. Symmetry, unchanged, though subject to changes. remaining invariant under certain changes. Yes, it's changed, but it has in it is remain to be in that structure, in a structure. It's like you can rotate it, you can translate it, but it still remain indifferent. Page 5, hard sphere and ball stick model. The the hard the hard sphere model, it means we use balls, right, solid, to form bigger solids. We use atom to model a to make the model. Why are we using it? Well, we simply glue the ball together, right? And in the ball stick model, we use smaller ball with stick. The reason why we do this is to make the to understand how a crystal, the construction of a crystal, right? So basically, ball stick model is a good way to study the lattice of a crystal, while the hard sphere model is it actually the model to study how the arrangement of no, not the arrangement. It somewhat is to study the actual structures of a crystal. Ball stick model is to study the lattice of the crystal, and while hard sphere model is to study the actual setup of the model. And the atoms in the unit cell that we studied earlier today, this right here is the whole crystal, right? And each of the cube here is the unit cell. Each unit cells is called at one corner of, each corner in the unit cells has 1/8 of an atom. This is a BCC. This is an example of BCC. Cube is usually to be used to be the unit cell. Okay, so next is the so there are two atoms in the body center cubic crystal, right? One in the center and one 1/8 in each of the corner. There are 8 corners, so 1/8 times 8 is 1. For FCC, so BCC crystal has 4 unit cell. Is made of 4 unit cell. There are 4 primitive cell in a BCC unit cell, and there are 2 primitive cells in 1 FCC unit cell. Why? Because here FCC has 4 atoms. Right? 1, 2, 3 plus 1 is 4. So we come back to page 6 in a minute, okay? Looking closely to page 6, we see that it only means to show that there is only 1/8 of an atom at each corner of the cube, and there's half of an atom that being stick on the surface of a cube, on the face of a cube. Going to the next slide, slide 7, APF of simple cubic structures. APF is standing for atomic pack factor, atomic packing factors of a simple cubic structures. The APF formula is equal to volume of the atom dividing by the volume of the cell. So we lattice we have to determine so R here standing for the radius of the atom, and A is the lattice parameter. So when in the second figures in page 7, right, it's show the lattice of a simple cubic structures. It shows that R is equal to half A. Why is R equal to half A? This is simple cubic structures, right? So that mean so we know that in BCC R is 3 over square root of 2A because it connects 4R together. But in the simple cubic structures, right? 2A is 2R is A is simply an edge of a cube. Yeah, I'm not sure why it's not like 2A equal to 2R. Oh no. So A is equal to 2R, right? A is 2R, that's why R is equal to half A. Right? 2R. A is always the edge. A is the edge of the volume. A is the edge of the volume, and R is the radius of an atom. So what I say is the edge of the cell is equal to two radius. The dot equal to the diameter of the atom. So that also means that one radius of the atom is half of the h parameter. The h parameter. So the volume of the cell is the cubic is the h to the cubic, right? To the power of 3. And there's one atom in simple cubic structures. So and the volume of one sphere is 1/3 pi to the time r cube. So 1 times 1/3 pi r cube over h parameter h to the third is pi over 6. That's how we should understand page slide 7. And on slide 8, it discuss about it show the it tell us that how metal on the periodic table have what are the structures of the metals in the periodic table. Structures that we know so far are CCP, standing for I'm not sure about this, but XCB is hexagon cubic, hexagon closed pack. Maybe CCP means center closed pack, and BCC body center cubic. XC is simply hexagon cubic. I'm not sure. So there is no FCC here. No metal in the periodic table has FCC. That's not right. Yeah, well, that's quite right. There's no FCC. Oh, FCC is gold, AU. Why is this like this? Center close pack, really? FCC. Why is this CC? I'm not so if gold AU is FCC. Why is this CCP right here? What does that mean? Let me figure it out real quick, okay? So I asked what is the difference between FCC and CCP, and the answer is FCC and FCC face center cubic and CCP cubic closed pack are closely related but not always identical depending on the context. FCC is a crystal. FCC is the crystal lattice type where atoms are located 8 corners of cube and a centers of all 6 faces. Each unit cell contains 4 atoms, coordination number 12, packing efficiency 74, metals like aluminum, copper, gold, nickel, and PT, crystalline, FCC, and CCP, closed pack, cubic closed pack. Well, it's a CCP is a way of describing atomic packing in terms of layers. In CCP, atoms are packed in the ABC stacking sequence. If you arrange sphere in closed packing, XCP, hexagon, closed pack, AB, stacking, CCP, ABC stacking. So XCP, hexagon, closed pack is AB, while CCP, ABC. The geometry of CCP stacking produces FCC unit cell. So geometry of CCP stacking produce FCC unit cell. So CCP is just a lattice showing the stacking sequence. So in another word, CCP is FCC. CCP is not unit cell. FCC is unit cell. FCC is lattice description geometric unit cell. CCP packing description layer stacking. So key difference between FCC and CCP is that FCC is the lattice description showing FCC is more like geometric unit cell, while CCP is more about packing description. It's about layer stacking. FCC is geometric unit cell and CCP is layer stacking. In practice, for elements in metal, FCC and CCP are the same structures but are ionic crystal. Like NaCl and ZnS, people sometimes distinguish FCC lattice of one type of ion, others occupying octahedral and tetrahedral voids. Okay, clear. So that's about page number 8. Alright, so page 9. the page 9 discussing about the representative of crystal structures. So the representative of simple cubic crystal structures is PO. How to what are the crystal structures of simple cubic? Is simply think about a matrix 333, right? In 3D 333 three atom in the x direction, three atom in the y direction, and three atom in the z direction. Yeah, and just connect the atom in a way that a small cube is being formed, and in a representative for BCC crystal structures is iron. BCC is of course body center cubic. Not sure if we should form a I'm actually not sure about this. What I see is a hexagon, and I don't think that's quite right. I'm not sure. And for FCC as well. Well, FCC is AB, right? Well, I don't really know about the crystal structures for each of these. They all seem like cube to me, but at some point not. Perhaps they use a bigger to form it. I don't know. For XCB, seemingly it's rotation. It rotates, right? Complexity to not. Let's not discuss about complex and diamond structures here. Too complicated. All right, let's come back to page number 9 later. Okay. All right, hang on. All right, guys, let's go discuss about page 10. Slide number 10, lattice and basis. Lattice is a periodic array of points. Each of the points has identical environment and can be related to each other by translational symmetry. In a few words, well, in short, lattice is an array of points. Right? So basically, it is a setup how, like the framework for. It's a framework. Lattice is like a framework. It defines how the geometry and the symmetry of the crystal of a crystal, right? If the lattice has a rectangular shape, then that's maybe the unit area of the framework, the symmetry of the geometry of the geometry of the atom setup. A lattice is being shown by dash and black point. And the basic are just elements, right? Atom, basic, base are elements. So think lattice like framework in construction. Like the structure, the bone, and basic are like muscle. So the muscle is being built on the bone structure. So the bases are being put in the the periodic array of lattice points in bases are being put on the symmetric environment of the lattice, the symmetric environment of the framework, right? Bases are the tie being put on the design in the place where we intend to put them in the symmetry, in the certain symmetry that we made it to be. All right.